Hello, everyone. We are doing the course Introduction to Pure Mathematics. Chapter number 18 is Equivalence Relations. I have also discussed this chapter in the course Group 3 for Beginners, but like here we will talk about it more deeply. So let's start. Maybe we need this one. Yeah. Relate SBS set a relation on the set S is defined as follows. That we choose a subset R of S of the Cartesian product S cross S. So in other words, R consists of sum of the ordered pairs S comma T with S comma T or elements of set S. Now for those order pairs, let's write that ordered pairs S comma T in R, we write that S is related to T, and say, as I said, S is related to T. And simply, for those order pairs which does not belong to R, we write S is not related to T. Thus, the symbol of this equivalence relates various pairs of elements of S. And it is called a relation on S, set S. Okay. This definition probably seems a bit strange at first sight, but let's define it more by a few examples. So, examples. let's say 8.1, sorry, 18.1. Okay. So number one, let S be the set of real numbers and define that A is related to B if and only if A is less than B. Here, the relation R consists those order pairs S comma T in the Cartesian product of R cross R, reals cross reals, such that S is less than T. Okay. Number two, let the set S is the set of integers and M be a positive integer, then define A is related to B if and only if A is congruent to B mod M. B mod M. Okay. Number three, let's say the set S is the set of complex numbers and A is related to B if and only if mod of A minus B is less than 1. And this is how we can express more examples. Let's say the set S is the set of reals again, and A is related to B if and only if A plus B is an integer. So for everything, you can define such R for every kind of. This is the property that there needs to satisfy, which will be here. Okay. Perfect. We can specify more examples by saying that, let's say that we have a set S which has only 1 comma 2 elements and an equivalence relation defined, a relation defined, not the equivalence relation defined by that 1 is related to 1. That means 1 comma 1 is an element in the relation R. 2 is related to 2. 2 is not related to 1. Sorry, this is 1 related to 2. 2 is not related to 1, but 2 is related to 2. This means there is a relation which consists elements S comma T, which consists elements like this: 1 comma 1, 1 comma 2. Now 2 comma 1 is not an element inside this relation because 2 is not related to 1. So we will just write 2 comma 2. Okay. Perfect. And we can further give a simple one, like say we have S could be any set, and we say that A is related to B if and only if A is equal to B. Okay. So the relations on a set S corresponds to the subsets of S cross S, Cartesian product of set S, and there is nothing much more to say about them in general. However, there are certain types of relations that are worthy of study. Is they crop up frequently. They are called equivalence relations. So we define them by a definition. Let's say we take a set and we write a relation on it, consider a relation on it. Be a relation on the set S. Then this relation is an equivalence relation if the following three properties hold for all elements of the set A, B, C in the set S. Those properties are, so number one property is A is related to A, and this says reflexive. Property two is if A is related to B, then B is related to A. And this is symmetric. Then we have if A is related to B, comma, B is related to C, or you can say and B is related to C, then A is related to C. And this is transitive. Okay. Now, let us examine each of the examples 18.1 for these properties. So the example again is examine the relations in example 18.1 for equivalency for these properties. Okay. So let's consider the first one where we had set is R, and we said that A is related to B if and only if A is less than B. Now you can say that A is less than B. So you can say that this is not reflexive or symmetric. Why? Because if a real number is less than to B, then a real number cannot be less than to from itself. So you can say that A is not less than A, and if A is less than B, then B is not less than A. These are the two reasons, but A is if A is less than B and B is less than C, then A is less than C. So this is transitive. But this means that this relation is not an equivalence relation. Okay. For number 2, so number 2 is that the set is, let me just write that, Z. This is too long. Set is Z, and M is positive. Yes. M is positive. And we said that A is related to B if and only if A is congruent to B mod M. So this is an equivalence relation. An equivalence relation by proposition 13.2, which says that A is congruent to A mod M. Reflexive, A is, if A is congruent to B mod M, then B is congruent to A mod M. And if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M. Okay. Number 3. So number 3 was that S is a complex number set and A is related to B if and only if mod of A minus B is less than, is less than 1. Now this is reflexive. This is reflexive and symmetric. This is reflexive and symmetric, which means that A minus A is less than 1. And it also says that A minus B is less than 1. Then B minus A is less than 1 in complex numbers. But it is not transitive. It is not transitive. And to see this, let's take A is 3/4, B is 0, and C is minus 3/4. Then Mod of A minus B is less than 1. Mod of B minus C is also less than 1. But mod of A minus C is greater than 1. Why? Because mod of A minus C is what? Is 3 over 4 minus into minus 3 over 4. And this is going to be 3 over 4 plus 3 over 4, which is greater than 1. So it is not transitive. Number 4 was that S is R and A is related to B if and only if sum of two reals is an integer. Now for this relation, we know that it is symmetric. This is symmetric as A plus B. If A plus B is integer, then B plus A is also an integer, but it is not reflexive and transitive. Because A plus A is not necessarily an integer, and if A plus B is an integer and B plus C is an integer, but it does not guarantee that A plus C is going to be an integer. Okay. And if you go further, number 5 was S had 1, 2, and the relation we had is 1, 1, 1, 2, and 2, 2. Now this is certainly reflexive and transitive, but not symmetric, because we have so this is reflexive because 1 is related to 1, 2 is related to 2. Transitive because if 1 is related to 2, 2, and 2 is related to 2, so there is no other element. So you can say that then 1 is related to 2. But not symmetric is 1 is related to 2, but 2 is not related to 1. Okay, perfect. Now, number 6 S is any state and A is related to B if and only if A is B. So number 6, S is any state and A is related to B if and only if A is B. This is an equivalence relation. Is A is A, and if A is B, then B is A, and if so, this is reflexivity. This is symmetric, and then if A is B and B is C, then A is C, and this is transitivity. This shows it is transitive. Okay, perfect. So we have learned that we can define relations on a state, and then we can define whether those relations are equivalence relations or not. Okay, perfect. We will end this part of the lecture here. In the next one, we'll talk about equivalence classes.